Creating beautiful interactive animations for the web can be easy. HTML Canvas allows dynamic, scriptable rendering of 2D shapes and bitmap images, and we can also make games using those same techniques. We can draw shapes with code, and today we will use vanilla JavaScript to draw a single line, and then we take it to the next level. There are a lot of things you can do with lines. For example, create a fully interactive, self-animating vector field that reacts to user input in multiple different ways. The main techniques we will focus on today will be how to make Canvas projects fully responsive with window resize event and cancelAnimationFrame method, how to improve code structure. We will focus on encapsulation and new JavaScript addition such as class fields and private class features. We will make sure periodic events in our animation have the correct timing with delta time, and as usual there will be some crazy experiments at the end, and I will share many other small front-end web development tips and tricks along the way, as I always do. Are you ready to improve your creative coding skills and become a better front-end web developer in the process? Then join me for this exercise in vanilla JavaScript, Canvas animations and object-oriented programming. I hope you get a lot of value today. My friend Radu helped me with some code optimizations for today's project. He is an expert on algorithms. Check out his channel in the video description. I will link some interesting project tutorials he prepared for us. I create a basic web page markup. I link my style CSS file. I create HTML5 canvas element with an ID of canvas1. That way I will be able to target it with CSS and JavaScript. And the last thing here, I need to link my script.js file, which will manage all logic and functionality. In style CSS, I do the usual global reset on margin and padding to override any differences between cross-browser default settings. And I set box sizing to border box, which will set elements width and height to include content, padding, and border. It does not include margin. All we do with CSS today is to position canvas. I give it position absolute, background black, top 0, left 0. Everything else will be done with JavaScript in script.js file. Before any code runs, I want to make sure everything on my web page has been fully loaded and is available for JavaScript to find. In this case, especially the canvas element. One way to do it is to call onload property on global window object. Sometimes you can also see people call onload on document object, which represents the web page. The difference is that with document onload, the event fires when DOM is ready, which could be before images and other external content is loaded. If you call onload on window object, JavaScript will wait for the entire page to load, including its content such as images, CSS, scripts, and so on. After my page has been fully loaded, I point JavaScript towards my canvas element. I need to capture it in a variable so that I can draw on it. I use document.getElementById here. Now I need to create an instance of built-in Canvas 2D drawing API, which holds all Canvas settings, such as fill color and line width, as well as all drawing functions, for example arc method to draw a circle, fill rectangle method to draw a rectangle, and so on. I will call that custom variable, for example CTX, shortcut for context, and I create my instance by taking canvas variable from line 1 and calling built-in getContext method. Keep in mind that getContext can only be called on a variable that holds a reference to HTML canvas element. It's a special method. I can pass it one of two possible arguments, WebGL or 2D. Today we will be using built-in 2D API. If you console log CTX, you will see all the properties and methods on there. If you console log canvas variable, it has width and height properties. I want to make my canvas cover full browser window, so I set its width to window.innerWidth and height to window inner height, like this. Today I want to show you how to avoid writing so-called spaghetti code and how to properly wrap your animations in objects. We will follow encapsulation principles as if we were building our own animation library. We will of course not use any libraries. All the code today will be plain vanilla JavaScript, and I will explain everything to make sure you understand and can write your own animation experiments. I'm going to create JavaScript class, which is basically a template for creating objects. Classes encapsulate data and then work on it with their methods, which is exactly what we will do today. Convention is to start class name with a capital letter to differentiate it from regular objects. I will call my class, for example, flow field effect. JavaScript doesn't really have classes like other programming languages do. Classes are just a syntax to simplify native JavaScript prototypes. Class is actually a special type of function, and same as with other functions, you can declare them in two ways. This is class declaration, and this is class expression. Both of these ways can be used to declare a JavaScript class. Important thing to note is function declarations are hoisted. Class declarations are not, which means you can't call the class before you declare it. JavaScript is changing every year and new syntax is being added. One of the latest additions are so-called class fields, which are basically properties that are held on your class, usually here on the top, and they don't depend on the constructor. Another new addition are private class features. Privacy could be applied to class fields or class methods by starting their name with a hash symbol. Until this change, convention was to write names of private class features with underscore, but these were still accessible from the outside. They were still fully public. With addition of private class features, if you start name with a hash symbol, privacy encapsulation of that field or method will be enforced by JavaScript, and you will get a syntax error if you try to access it from outside the class. The only way to get a value of private class field from the outside of class is to create a public method on that class that returns this private value. I will show you how to do that, since we will need to use all of these techniques to create animation loop and event listeners within this encapsulated code structure. We will take it step by step and we will experiment a bit to see how everything works. Don't worry, it's easy. This course is beginner friendly. I will create 3 private class fields, CTX, to specify what canvas element we want to draw on. In case we have multiple canvas layers, we can bring all of them here like this. I will also create fields for width and height, so that we are not taking these values from the outside. We don't want to be using global variables inside our classes if we can avoid it. We can do this 2 ways. I can assign values to my private class fields directly in this area, or I can do that inside my constructor. I need these values to be passed as arguments to my constructor first, so we will go with the second option this time. Let me show you. Constructor is a special mandatory method every JavaScript class needs to have. It will just run once at the point when we create an instance of the class by calling it with the new keyword. We will do that in a minute. My constructor will expect 3 arguments coming from the outside: CTX, width, and height. Inside the constructor, I take the private class field from line 9 and I assign it to CTX that was passed to my constructor. I do the same for width and height. When I create an instance of this class in a minute, I will pass it CTX from line 3, canvas width and canvas height as these CTX, width and height arguments. And constructor will convert these global variables into private class fields. This is how you can create encapsulation in your project and avoid using global variables inside your classes, because I could also be pulling CTX variable from line 3 into drawing code inside my class directly, but that would be considered a bad practice. Doing it the way I'm showing you today is how animation libraries are made, for example. Important thing to note about private class fields is that you first have to declare them in this area before you assign them values inside the constructor. If I don't declare them here and just write this line, I will get a syntax error. You can execute code or even call class functions at the point when class is instantiated with the new keyword and constructor is called to create a new object. Let me show you what I mean. I will put console log inside my constructor that says effect loaded, for example. Inside onload event, I can create a constant variable. I call, for example, flow field, and I set it equal to new flow field effect, like this. The new keyword is a special command in JavaScript. It will look for class with the same name, and it will run its constructor once. Constructor creates one new blank JavaScript object and assigns it values and properties as declared in the blueprint here. I can see my class constructor expects CTX, width and height as arguments, so I pass it CTX from line 3, canvas width as width, and canvas height as height. In console, I can see the console log from line 17 was triggered, so I know I successfully created an instance of my flow field effect class. Notice here, we took CTX from line 3 and we passed it to our class constructor, converting global variable into a private class field. This is encapsulation, one of the main principles of object-oriented programming. Encapsulation is the bundling of data and the methods that act on that data in a way that access to the data is restricted from outside the bundle. So let's create a private class method that will act on our data. I will call it draw, and I start its name with hash like this. This means this is a private method. It cannot be called from outside this class. It can only be called from somewhere inside this class, usually to manage some kind of internal functionality, such as calculating a value and so on. In this case, draw method's job will be to draw a single frame of my animated effect. We will start simple to make sure it's very clear what's going on, before we scale it up into a complex interactive animation. At first, the only job of this draw method will be to draw a single line, and it will take two arguments coming from the outside for x and y coordinates for a starting point of this line. To start drawing a shape, I take this.ctx class field from line 10, which holds a reference to my canvas drawing context, and I call beginPath built-in canvas method on it. This method simply tells Canvas we want to start drawing a new shape. If we were drawing a shape before this one, beginPath will close the previous shape and start a new one. To draw a line on Canvas is very simple. We use built-in moveTo method to set starting x and y coordinates. Our line will start at x and y coordinates that were passed to draw method as arguments here. Then we call built-in line2 method, which will set the endpoint coordinates of line. We can also call line2 method many times to create a more complex shape, like I did in a recent course to draw animated stars and polygons. Endpoint of this line will be the initial x position plus 100 pixels and the initial y position plus 100 pixels. Finally, we call built-in stroke method, which will draw the actual shape we just mapped. If I want the line to be drawn at the point where I create instance of my flow field effect class, I can just call draw method inside constructor like this. Draw method expects starting x and y coordinates, so I pass it 10, 10. By default, stroke style is set to black and we have black background, so inside constructor I set stroke style to white. It goes from starting coordinates in moveTo method to ending coordinates in line2 method. I can change these values however I want, and the line will be drawn between these 2 points. I could also create a variable called length. I set it to 300, and I replace hard-coded values on line 25 with this new length variable. Now I can change the length of my line here. We have built a solid boilerplate drawing code base, and we can do so many different effects and animations here now. Notice that I'm running private draw method by calling it from inside constructor, which is being triggered here on line 6. I'm calling private draw method from class constructor, which is public. My public constructor enables access to private draw method from the outside. Right now, it just draws a single static line. What about if we want to make it move? How do we create animation loop in a code base like this? This time it will be a public method, so it can be called from outside the class. I call it, for example, animate. I take draw method from line 19 and I put it inside animate. I remove this console log. Inside animate I put another console log that says animating. So again, I'm calling private draw method from inside public animate method. I could call animate from inside constructor to run it when class instance is created, but I can also call it from the outside since it's a public method. On line 6 I have my custom flow field variable that holds an instance of flow field effect class. I can say flowField.animate to call its public class method. If I called flowField draw from here, I would get a syntax error because a draw method starts with a hash symbol. It's a private method and privacy is enforced by JavaScript with this syntax. Private methods cannot be called from outside their class directly like this. So we called animate and we can see the line. I can also see console log that says animating. It is not actually animating, we just called the method once and it drew a static line on canvas. To animate something, we need to be calling animate over and over to create animation loop. The best way to do it is to use built-in requestAnimationFrame method. It takes one argument, which is the name of the function we want to call. I pass it animate, the name of its parent function. Doing that will create an endless loop because we call animate first here on line 7. It will run its code and requestAnimationFrame will call it one more time. It will run its code again and requestAnimationFrame will call it again. We have an endless loop here. JavaScript also has a built-in setInterval method where you can give it a function and amount of milliseconds and it will call that function over and over in that interval. RequestAnimationFrame is better than setInterval for creating web animations because it automatically adjusts itself to screen refresh rate in most browsers. Usually it runs around 60 times per second, unless you have high refresh rate screen. If I run the code, I get an error. In console, I can see my error is on line 30. It says animate is not defined. It's because animate is a method on a class. I need to refer to it with this keyword. When I run the code again, I can see we get one loop because it gives me one console log. But then on the second loop, we get uncode type error. Cannot read properties of undefined on line 28. We have a problem with this keyword. We are calling animate on line 7, and on the second loop, JavaScript forgets what this keyword represents. It forgets that this keyword is our flow field object. To make it remember which object this keyword is pointing to on consecutive runs of animation loop, I need to bind it. Bind is a built-in JavaScript function which takes at least one argument, and that argument sets what object this keyword refers to for that upcoming function call. I'm basically saying call this.animate and remember that this keyword represents this flow field effect object, so make sure you keep information about its properties and methods in memory for that upcoming function call. Scopes and closures are one of the most complex JavaScript principles, so be patient and take your time. It takes a while to fully understand it if you are a beginner. If I check my console now, I can see we have successfully created animation loop and it's running over and over, drawing the same line on canvas 60 times per second. When you animate something on canvas, you basically draw it, delete it, update its position and draw it again. This will create illusion of motion. To prove that the line is animating, I can for example create this.x and the this.y properties and set them to 0. I pass them to draw method on line 30, and for each animation loop I increase x by 2 pixels and y by 0.5 pixels. And our line is animating. I can change the values. It looks like this because we see old paint. We are not deleting old lines, so it creates a path like this. For our effect, I only want to see the current animation frame, so I will use built-in clear rectangle method to clear the entire canvas between each frame. I want to clear the entire canvas area, so from coordinates 0, 0 to coordinates this.width and this.height. Now we can just see the current animation frame. When I resize browser window, my black canvas doesn't automatically resize with it, it stays the same size. How do I make sure my canvas animation is fully responsive? Upon line 10, I will create an event listener for window resize event. This event fires every time user changes size of browser window and it will run its callback function. In the callback, I have to set canvas width and height to the new window size. Simple. When I trigger resize event, I can see we have a scope issue. Because canvas variable is declared inside onload function, if I put resize event listener on a global scope, it won't be able to see it. I can fix it, for example, by putting resize event listener inside onload event, or I can bring my canvas variable one level up on the global scope. On line 1, I declare let variable called canvas, and here I remove const keyword, so we are no longer declaring new variable. We are just assigning value to canvas variable from line 1. I create another let variable called ctx and I do the same thing. Now canvas is assigned to the correct canvas element only after the page has been fully loaded, but at the same time it's globally available across my application. As you can see, resize event fires correctly and adjusts canvas width and height to the new dimensions as I'm resizing browser window. It is also distorting and stretching my drawing, so I have to create a new instance of flow field effect class, since we are passing it width and height and those values have changed. Again, I bring it one level up to a global scope first, and here on line 10 I assign instance of flow field effect class to that existing variable from line 3. Whenever I resize browser window, I create a new instance of this class, because I need to pass it the new updated canvas width and canvas height, to make sure my animation is aware of what area of canvas is available for it to draw on. And since this is a new instance with different values, I need to call its animate method. Now I'm doing something very bad. Every time resize event fires, I'm creating a new instance of flow field effect class and I'm calling its animate, which has its own requestAnimationFrame method, and it runs an endless loop. I am now running multiple animation loops at the same time. In console, I can see the console log inside animate is being called a lot. We need to cancel the previous animation before we create a new one. We are creating animation loop here on line 46 with built-in requestAnimationFrame JavaScript method. There is another method called cancelAnimationFrame, which simply cancels previously scheduled animation frame request. All we have to do here is to make sure we pass a reference to it correctly so that it knows what to cancel. I will hold that reference in a variable to make it very easy. I create another global variable called flowFieldAnimation up on line 4, and down here on line 47, when I create AnimationFrame request, I assign it to this new variable. If I run the code now, everything still works the same. Doing this didn't break our animation loop. Good. When Resize event fires, I take this flowFieldAnimation variable from line 4, which holds a reference to the next animation frame that is about to be drawn, and I pass it to cancelAnimationFrame method, like this. When we resize, I cancel old animation request, resize canvas to match the new window dimensions, create new instance of flowFieldEffect class, and I call animate to create new request animation frame loop. What if I want the line to start from exactly in the middle of the screen? I will pass my draw method width divided by 2 and height divided by 2. I'm no longer using this.x and this.y, so I delete this code and this code. We are still animating a static line. I could also use a little bit of trigonometry here. Starting x coordinate will be width of canvas divided by 2, so in the middle, plus built-in math.sine method, which expects angle value in radians. You can use math.sine for any kind of wavy movement in your animation and game projects. All you have to remember is that math.sine expects a value of angle in radians as an argument, and it will map that value somewhere along a sine wave. If you pass it ever-increasing angle value, it will create endless wavy movement that goes back and forth between -1 and +1. I will pass it this.angle property, and I create it on my class. And for every frame of my animation loop, I increase this.angle by 0.1. It just moves between -1 and +1, so the movement is hardly visible. You can multiply it by radius to create a larger value range in your sine wave movement. I can also add it to my starting y coordinate. If I make the second call cosine, sine and cosine will work together to map a circular path. If you are a beginner, don't feel like you need to fully understand trigonometry. For animation purposes, just remember, if you pass it ever-increasing angle value, it will map a wavy movement between -1 and +1, or whatever value you give it as radius. Here I'm using radius of 100 pixels. We will also use trigonometry for rotation, but I also want to show you how to make your animations interact with mouse position. First, on a very simple example, and then we will take it to the next level and make it react to mouse in a big way, where mouse position completely changes the final effect. I create a constant variable called mouse, and I set it equal to JavaScript object. This object will have x and y properties, which will represent current mouse coordinates. First, I set them to 0. I create a Mousemove event listener. Event listeners have access to a special built-in event object. It's auto-generated every time the event fires, and we can access it by giving it a variable name here. I will call it, for example, e. Inside, I console log this e variable. First, I will comment out the other console log we have on line 53. I will also comment out this line to stop animation for now. Right. Now, if I move mouse over canvas area, my Mousemove event listener fires, and it console logs this auto-generated event object. I can open that object and I can see it has all kinds of different properties that give me very specific information about this particular tick of Mousemove event. What I'm interested in are these x and y properties. Every time a Mousemove event ticks, I will take mouse.x property from line 24, and I set it equal to x property on this event object we just inspected in console. I do the same for mousey from line 25. On line 53, inside animate method, I remove math.sine and math.cosine, and inside the draw method on line 47, I set ending coordinates of the line to current mouse x and y positions. Now we have interactive line connecting middle of canvas to the current mouse position. I can change some canvas settings, for example line width could be 5 pixels. If I comment out clear rectangle from line 53, we can see old frames and we can draw shapes like this. For the following effect, I only want to see the current animation frame. Let's use clear rectangle again. Before we make our effect more complex, very important thing, Especially if we have things moving around, you don't want our animation to move fast on a new computer and very slow on older PCs, just because the new computer is able to serve frames much faster. We make sure animation runs at the same speed on each machine by measuring so-called delta time. Delta time is the difference between the current and the previous animation frame in milliseconds. To calculate it, I will need a property that will temporarily hold a timestamp value from the previous frame. I will call it, for example, this.lastTime. To get a timestamp is very easy if you are using requestAnimationFrame. In a similar way how event listeners automatically generate event object with information about that event, requestAnimationFrame automatically generates a timestamp value that is being passed to the function we call using requestAnimationFrame, in this case our animate method. It's being automatically passed there, and I can access it by giving it a variable name. I will call it, for example, timestamp, like this. So this timestamp is telling me when was this particular animate method called by requestAnimationFrame. To calculate delta time, the difference between this frame and the previous frame in milliseconds, I take timestamp from this loop minus timestamp from the previous loop, which I will be saving in this .lastTime property from line 43. So each time requestAnimationFrame serves the next loop of animate, it passes it automatically generated timestamp. I use that timestamp to calculate delta time by taking this current timestamp minus timestamp from the previous loop, and when I have delta time value, I override this .lastTime from line 43 with the value of current timestamp to make it available to calculate delta time in the next upcoming loop. If I console log timestamp, you can see it's giving me value in milliseconds since the start of the first animation loop. If I console log delta time, the difference in milliseconds between frames, most modern computers will give you around 16.6 milliseconds, which is 1000 milliseconds divided by 60 frames per second. If your computer screen has high refresh rate, you can get a lower delta time value here. If you have old PC and your computer is struggling with animation, especially later when we create more complex effects, you might get higher value of delta time, or you might get spikes. It doesn't matter, because if we have this delta time value, we can tell our computer how many milliseconds we want to pass before the next animation frame is served. If we have a slower computer, frame rate might be lower, but delta time will allow us to synchronize movement and animation speed so that timings are the same on all machines. Timestamp is generated when a function is called by requestAnimationFrame. RequestAnimationFrame inserts that timestamp as an argument to animate function, so we have to keep in mind that only the second loop is triggered by requestAnimationFrame. The initial first call of animate will not have timestamp argument passed to it, so we will pass it 0, just for that first initial frame. I delete this console log. We can use delta time when something is moving around in a certain speed, but also for something that happens in a certain interval, periodically, such as serving the next frame of our animation, but also adding a new animated object or something like that, something that happens over and over in a certain interval. To use delta time this way, we will need two helper variables. One will hold an interval value of that periodic event in milliseconds. I will call it this.interval, and I want my repeating event to be triggered every 100 milliseconds. The second helper variable will be a counter that will add delta time for each frame over and over, starting from 0, until it accumulates the amount in the interval variable. At that point, it will trigger the event and reset itself back to 0 so that it can start counting again. Doing this will allow us to make sure that events in our codebase are triggered at the same interval. Let's say I have interval of 100 milliseconds. On a fast computer, delta time is 16 milliseconds, so it will jump by steps of 16 milliseconds until it reaches 100, and it triggers the event. Somebody might have a slower computer. Their computer will have higher delta time, for example 50 milliseconds, because their computer is not able to serve animation frames so fast for some reason. Faster computer will have to tick 6 times, run 6 animation loops before it reaches 100 milliseconds interval in 16 millisecond steps. But slower computer will have to tick only twice to reach 100, because each step, its delta time is 50. 50 plus 50 is 100. This will even out the difference in their performance, and in the end, the repeating event in our codebase will be triggered at the same or in the very similar time period. So with this in mind, I want to draw a new animation frame every 100 milliseconds. I say if this.timer from line 45 is more than this.interval from line 44, only then run all this drawing code. When you run it, reset timer to 0 so that it can start counting milliseconds again for the next time. Else, just increase this.timer by delta time and don't update my drawings. This is periodic event based on delta time. Updating our animation every 100 milliseconds is just 10 frames per second. It will be laggy. I could also do 500 milliseconds, which is just 2 frames per second. 1000 divided by 2 is 500. If we want smooth animation, we set this.interval to 60 frames per second. 1000 milliseconds divided by 60, which is roughly 16.6 milliseconds. Vector field usually looks like a grid where each cell has a line of certain length that points towards a direction. I create a cell size property on my class which will represent how big individual cells in my grid will be. I want grid with cells 15 × 15 pixels, for example. I rename my draw function on line 48 to draw line to more accurately represent what is the function doing. I also need to update it on line 61. I delete the reference to this.angle here and here. Now I want to map a grid 15 × 15 pixels all over my canvas, and inside each of these cells I want to use my drawLine private class method to draw a smaller line. We can create a grid on canvas with nested for loops, which means loop inside of another loop. The outer loop will go over canvas row by row from top to bottom. It will represent vertical y coordinate of each cell. We will start up top at vertical coordinate 0, and we will go down row by row until we reach height of canvas. Here I'm mapping a grid, so rather than going by 1 pixel each time, we just jump to a new row. We will jump by the amount of cell size from line 45, in our case 15 pixels. So the outer loop will manage rows. Each time we enter a new row, we will map horizontal cells there by going from left to right, jumping by the amount of cell size again. We will start at horizontal coordinate 0, and until we reach width of canvas, we will be jumping by cell size 15 pixels. Inside, we will call drawLine from line 47 each time we enter a new cell in our new grid. That line will start at the horizontal x coordinate of that cell, with x value coming from the inner loop and y coordinate coming from the outer loop. I want just a simple short line for now, so let's say 5 pixels to the right and 5 pixels down from the starting position. So what I just did here, imagine these cells are larger just for the purposes of this visualization. Outer loop enters a row with vertical position y. We enter inner loop and we map horizontal positions on that row, going from 0 to canvas width, jumping by cell size of 15 pixels, from left to right. When we reach the end, we exit the inner loop, enter the outer loop, y increases by 15, we enter inner loop again, and we map that second row from left to right. Again, we exit the inner loop, y increases by 15 again, and we map each row until y reaches the height of canvas, so bottom of the page. This is how you map a grid on canvas using nested for loops. I can change length and direction of lines by changing values here. I can also change number of cells in a grid by changing value in cell size property on line 45. Direction of lines depends on x and y values we pass to line2 method. So as we said, private class methods have names that start with a hash symbol. They can be called from within the class to manage some kind of internal functionality. I can, for example, create another private class method to create gradient. I call it create gradient, for example. Inside constructor, I create a property called this.gradient. Inside the new method, I take this.ctx from line 37 and I call built-in create linear gradient HTML canvas method. It expects 4 arguments. The first 2 are starting coordinates and the last 2 are ending coordinates of a line. That line will represent size and direction of the gradient. I want it to go from top left corner, so coordinates 0, 0, to bottom right corner, so canvas width, canvas height. To map colors along the gradient, we can use special built-in addColorStop method, which can only be called on a variable that holds a reference to canvas gradient. addColorStop needs 2 arguments. The first argument is offset and it's a value between 0 and 1. It will define where along the gradient we want this color to be. 0 is start, 1 is the end. It can be any value in between. The second argument is the color. So I have 2 color stops here. The first will be at 0.1 offset and color will be FF5C33. The second color is at offset 0.9 and I will use FFFF33. Now I can call this custom private createGradient method from line 49 inside my class constructor, which will execute it as soon as I instantiate flowFieldEffect class with the new keyword. I'm getting this error in console because I didn't put hash symbol in front of hexadecimal color value here. When we created our gradient, we can take stroke style and assign it to this.gradient from line 45. I can add more color stops. I'm gonna make additional color stops at 0.2, 0.4, 0.6 and 0.8. And I will intentionally go for lighter colors since I want them to contrast against the black background. I can change line width and I can play with cell size to create simple patterns like this. I can also pass additional angle property to draw line on line 73, and I need to make sure drawLine function expects it as an argument on line 58. That angle will be coming from my for loops here. I can, for example, calculate it by calling math.cosine and passing it x from the inner loop, plus math.sine and passing it y from the outer loop. Then we call drawLine, passing it angle, and inside drawLine I will use that angle to change ending coordinates we pass to line2 method. By default, these are very small values, so let's try and multiply them by radius of 100. Maybe 20? I can also multiply it by some random number here just to see how it affects the pattern. To actually make each line rotated based on its x and y position, I can actually just say x plus math.cosine and I pass it angle, and y plus math.sine and I also pass it angle. Again, these are very short lines, so I multiply them times 20, for example. Now we are starting to get more interesting pattern. Originally, I was using built-in translate and rotate canvas methods to achieve the same thing, but thanks to my friend Radu, we found out that replacing translate and rotate with sine and cosine and passing it at the same angle value will also result in rotation effect, but it's much less performance demanding, so it will run smoother when we animate it in a minute. Radu is an expert on algorithms. Check out his channel. I will link some of his interesting project tutorials in the video description. So to make it clear what's going on, by including x and y position in sine and cosine, the lines rotate around based on their position. As we go from left to right and from top to bottom, lines are slowly rotating and it creates a pattern as a result. If I multiply it by a smaller number, we get less angle rotation between each neighboring line, which affects the size and resolution of the emerging pattern. Now we have something that could be called a vector field. Each cell in the grid has a line with certain length and direction. Now I could just throw some animated particles on canvas and make them flow around following these vectors, these lines. Speed and direction of movement of each particle would depend on length and direction of line that the particle is currently flowing over. And that is a principle of flow fields. Right now, we are creating a regular circular repeating pattern with trigonometry. You can also use more complex algorithms than the one we just used. For example, a very common one used here is Perlin noise or simplex noise. This will give you random but very natural looking flow pattern. Values here on line 73 affect kind of how close we are zoomed in to the pattern and also ratio between its vertical and horizontal scale. Changing this radius value on line 62 changes the length of lines. Now the lines are longer than individual cells, so we are getting some areas with overlap, making the pattern slightly more prominent. I can zoom into the pattern by multiplying by a smaller value here, or I can zoom out by multiplying by larger decimal values. I can also wrap this whole block in brackets and multiply that by some radius, which will affect how much is the emerging pattern curving in on itself. Let's try to change line width. Smaller cell size will give effect more detail, but also it's more demanding on system to draw, so keep that in mind. If at any point from now you start getting performance issues because we are drawing a lot of lines, making this cell size value a larger number is the easiest way to increase performance and render speed of your effect. Anything over 15 pixels should be safe. Anything under that value and you might notice some FPS drops, I think. We will see when we start animating and moving this effect around based on periodic events and user input. Definitely don't try to animate it with 3 pixel cell size. Rendering this as a static image would be fine, but drawing, updating and animating each line like this 60 times per second will be a challenge for most computers. If you are having performance issues right now, increase the cell size value until your computer can handle it. Let's experiment some more. Look how this radius value changes how the emerging pattern curves in on itself. When I slowly increase it, do you see what's going on? What if I want to make this movement automatic and I want it to slowly animate like this on its own? I increase cell size to something safer, for example 15 pixels. I set line width to 1 pixel. Line width also affects performance with some effects on canvas. Bigger and thicker lines take more system resources to draw, so keep that in mind. I replace this hard-coded value we just played with a variable. I will call it, for example, this.radius. I declare it as a property on my class constructor. Initial value can be 10 or maybe 5. I want this radius value to automatically increase by a very small amount for each animation frame. I create additional property called this.vr, velocity of radius, and I set it to 0.03. Initially, I set radius to 0. Inside my animate method, I increase this.radius by this.vr from line 49 for each animation frame. Now we can properly see how this value makes this pattern spiral inside and create more curves. Keep in mind that all we are looking at right now is just a grid of lines that are rotating around based on their vertical and horizontal position. In areas like here, where there isn't much overlap, it's very clear to see what exactly is each individual line doing. I can reduce cell size to make the effect look more detailed, but be careful here, don't use very small numbers here. Also, size of our canvas will affect performance in this case, since larger canvas means more lines, which means more calculations and draw calls that need to happen per frame. At a certain point, I want the spiraling to stop and start going in the opposite direction, so that we have effect that endlessly bounces back and forth between a certain value range. This following technique can also be used for bouncing movement or whenever you want something to go back and forth between two values. We are adding this.vr to radius endlessly on line 72. I can simply say if we reach a certain range limit, flip it to the opposite value. So if it's positive, make it negative. If it's negative, make it positive. Since we are adding VR here, if VR becomes negative, it will start going in the opposite direction. I say if this.radius is more than 5, or if this.radius is less than -5, flip this.vr to its opposite, so from positive to negative, or from negative to positive by multiplying it times -1. When we reach the limit, both maximum or minimum limit, it will flip the direction by multiplying it times -1. The correct syntax here is actually times equals -1. So now we go all the way to +5, then it flips, goes past 0 to minus value. When we reach -5, we flip again, and now we have endless animation bouncing between -5 and +5. This hard-coded value of 30 is actually length of lines, so let's use my length variable here instead. If I set length to 10, the lines are very short. I increase cell size to 15, line length to 15 as well, so now it's the same as cell size. Length 20 and we are starting to get some overlap, and the swirly pattern becomes more visible. We can also make line length dependent on some variable input, for example on position of the line, or even based on current distance of that particular line from a mouse cursor. That could look interesting, let's try that. I create a custom temporary variable I call for example position x, and I set it equal to x passed on line 60 as an argument. And I do the same for position y. We already created mouse object that has x and y properties based on the current mouse coordinates. I want to cycle through all my lines in this effect and calculate their current distance from mouse cursor. To calculate distance between 2 points is easy with Pythagoras theorem formula. We have 2 points, one point is mouse cursor, the other point is starting x and y coordinates of a line. To calculate the distance between these 2 points, I calculate their distance on x-axis and y-axis separately, which will give me this imaginary right triangle. Since I know this side and this side, and I know this is 90 degrees, I can use Pythagoras theorem to calculate this side, which is the actual distance between the 2 points. What does that look like in JavaScript? First, I calculate this side, distance between mouse and start position of line on horizontal x-axis, dx, distance x. Then I calculate dy, distance between mouse and start position of line on vertical y-axis. That gives me two sides of right triangle, and I know the angle between them is 90 degrees. Pythagoras' theorem gives us a formula to calculate hypotenuse, the longest side of the right triangle, which is at the same time the distance between my 2 points, mouse and starting point of the line. The formula is square root from dx times dx plus dy times dy, or dx squared dy squared. Since I need to calculate this distance between mouse and each individual line in my effect for each frame of animation, I will skip the square root calculation because calculating square root is a very performance demanding operation. It will still work, we will just have to work with much larger numbers since we are not square rooting them. So we have distance between mouse cursor position and position of each line. It is held just temporarily here, and we will use it to draw lines of different lengths. I do that by assigning distance to length. Length is used here to draw lines, if you remember. That will give us extremely long lines. We need to make them much shorter. Length could be, for example, distance divided by 10,000. I have to use large numbers like 10,000 here because we skipped square root. Also, I'm dividing it by 10,000. Maybe a better idea would be to multiply it by a very small number. Again, for a performance reason, multiplication in JavaScript is more efficient than division. This is starting to look really interesting. We have a grid of lines that are rotating in a pattern based on their x and y position in the grid. They are auto-rotating within a certain range, back and forth, and at the same time they react to mouse movement. I hope you are getting some value since these creative coding techniques can be used to create thousands of completely different effects. We covered a lot today, but we are not done yet. Let's take it another step further and make it even more reactive. First, I will cap the minimum and maximum length of lines because on large screens, the distant lines can get very long, covering and interfering with the rest of the effect. I will just do a simple if statement here. If distance is more than 150,000, keep it at 150,000. This will not allow it to go any higher. Okay, that's too short since we are then dividing that value. Maybe 300,000? Still too short. 400? 500? That's alright. Also, I do else if to cap minimum length. You don't have to do that if you want your lines to be extremely short around the mouse. I'm just experimenting now. I set minimum value to 100,000. Maybe maximum to 600,000. Yes, that's better. And minimum 50,000. Look at these two values here. They affect how zoomed in or out we are on the pattern, and ratio between these two numbers determines how stretched the pattern is horizontally or vertically. If I keep them the same and use smaller number, we zoom in. If we multiply by a larger number, we zoom out of the pattern a little bit. What happens if I include mouse X here and mouse Y here? Now, these numbers are very large and it's making the angle values too large and lines rotate so much the pattern is lost. I can scale it down by multiplying it by much smaller numbers. Now, line length reacts to distance from mouse, and at the same time we are scaling and stretching the effect based on mouse X and Y position. This feels very interactive. If anything, it really shows you how we can zoom in and out of the pattern and how it can be stretched and scaled vertically and horizontally. We could also attach these values to sliders, for example, to generate certain more static setup if that's what you want. You can do that as a challenge if you think you're ready. And if you don't think you're ready, you can always watch more of my videos and get more comfortable with Canvas and JavaScript. I disable the automatic radius animation and I set radius to a static value of 3, for example. Or maybe 6. Now, the pattern itself is stable and we can better see how going from top left to bottom right zooms on it and how stretching it vertically and horizontally affects the final outcome. This is a lot of interactivity. I uncomment the automated radius. It's stuck now because I set the initial radius to be outside the range we defined on line 80. Easy fix. If you are a beginner, you should be really proud of yourself right now. We used so many animation techniques today and we went really far from drawing a single line on canvas. You can do so many other different animations and effects with this codebase, for example flow fields. If you are curious to see what else is possible with built-in Canvas drawing methods, check out my playlists. I'll see you there.